All right, welcome back. Next technique to cover is the method of substitution. So what happens if the power rule fails? Well, you can move on to this technique, and if this one doesn't work, you can try something later. In any case, let's take a look at 4 examples that involve the method of substitution. So here is our first example. This is an indefinite integral. As you can see, we're still talking about indefinite integrals. In this example, notice that we have a bracketed quantity that is raised to some power. In this case, it would be prohibitive to try to expand this all out. Can you imagine expanding that out to the power of 10? That's a really, really nasty binomial expansion. Perhaps we can try to change the variables, and in this case, we can simplify the problem. And that's exactly what the method of substitution does. Let's just make a guess here that we could replace the quantity in the brackets with some other variable u like that. Now you might say, well, what if that doesn't work? In this case, it's going to work. And in the examples I show you, it will work. But in future situations where it doesn't work, we would try something else. In this case, though, it will work. Notice that we have u, which is our new variable, and we have our old variable, which is x. Your objective now is to turn all of the x's here into u's. So how do you do that? Let's find the derivative of this equation here. So if we take the derivative with respect to x, we end up with, let's take a look here, we end up with 2x. There you go. We're going to write this another way called a differential form. So what you do is you quote unquote move the dx to the other side. It's not quite that simple in terms of its logic, but in terms of how we're going to apply it here, it works like that. Your objective now is to use this information here and this information here and to change all the x's into u's. So let's take a look carefully here. Okay, well, I see 2x and I see dx. Well, that's good news because that's exactly what we have here. So we can replace 2x and dx, just like those things that I've circled. Well, we can replace them with du. So I'm just going to write a du there. How about the quantity in the bracket? Take a look at that stuff there. Okay, so there we have this thing here, which is actually just u. So that's u to the 10. And then our regular integral symbol. So there you go. You see everything now is in terms of u. Again, this question is somewhat artificial in the big scheme of things. It works out. And if it doesn't work out, we'll try other methods in future videos. In any case, this integral just becomes a power rule, which we know how to do from earlier as adding 1 to the exponent, so 11 there, and dividing by the same quantity. Don't forget your constant of integration. Ultimately, we have what we need, and we can present the answer using the quantity or variable x. So let's just replace the u there with x squared plus 5. And that is your final answer. Okay, well, if I can write it faster, there we go. Let's try a few more examples. I've tossed in some polynomials in terms of the bracketed quantity, and I've also introduced some radicals in future examples. And moving on to this one here, we again see a quantity in brackets raised to some power, and then we have some quantity on the outside. The hope is that the derivative of whatever that stuff is there would be a multiple of what we see here. Let's try that out. We're going to let u equal the stuff in the brackets right here. So if we let u equal 3x squared plus x minus 5, let's apply the differential form, which is to find the derivative of this, but to move the dx to this side as well. So here we'll write du, and that dx that was below, I'm going to bring it to the other side. So the derivative of the right-hand side is 6x plus 1. And we can put the differential of x there on the right. Notice that this is very convenient. Again, somewhat artificial, but good for training you in the beginning. So there you go. The stuff in the circle there, 6x plus 1 and the dx, so that quantity that I've written there is exactly what we see as du. So let's just write du there. And I'll just circle that as well. Now let's take a look at the quantity in the bracket. Well, this thing here is exactly what u is. Well, because we've designed that. So we have u to the 4. Okay, we can proceed. Let's add 1 to the exponent using the power rule, the very first lesson that I showed you. And then we can rewrite the u in terms of x by using the original substitution. Some of these questions are so elementary, I don't mean simple, but they work out well that you could actually just guess the answer. So for some of the students that I do teach in my day job as a professor, I do tend to use a method called guessing and checking. And that method just comes down to the fact that it's really easy to see this pattern if you can just do this derivative in your head. Anyway, moving on, let's try a question that has a radical. Okay, so this thing here might scare you, but just remember, what is a root? A root is essentially an exponent. So that's 8x plus 1, and the square root in this case will be the half. In fact, the next example, I'll toss in a cube root. So we'll see how that goes. Let's not forget the dx. Let's let u equal the quantity in the bracket. So we have u equals 8x plus 1, and let's apply the differential here. So we have du, the derivative of that with respect to x is just 8. And don't forget, we put a dx there. Now, things are not as simple as before. So what can we do? Well, we have a couple of things here that are looking a little bit messy. This x here, well, it doesn't really go away because there's no x in the differential form. So we got to be a little bit more creative in this example, but don't worry, we'll figure it out. So what I'm going to do is try my best to replace all these x's with u's, beginning with this. I notice that we have a dx here, and I notice that we have a dx there. So what I can do is I could rewrite this as dx is equal to du over 8. So that dx is dealt with as du over 8. Then we have a 3. Nothing to happen there. That's pretty boring. So let's put an arrow for the 3. This x is going to be the thing that's a little bit messed up. But this quantity here in the brackets is pretty safe because that's just u to the half. So we have to deal with just this x. This x, this little weasel over here, that is the problem. So let's deal with that problem by using the original substitution. What I'm going to do is I'll just work myself up here a little bit. And what I'd like you to do is solve for x. Now, you're taking a calculus course, I'm assuming, so this should be something that you could do in your head. So I am going to do that in my head, or at least in one step on this screen. So that's u minus 1 divided by 8. And there you have it, u minus 1 divided by 8. Okay, well, that's looking a little bit more promising. What we can do now is kind of filter out all the numbers, the 3's and the 8's. I'll do that here. So we have a 3, 8, 8. So 3 over 8 over 8, that's 3 over 64. And then what I want you to do is expand this. So you see the u to the half and then the 1 here. So we're going to multiply u to the half by u. So that's adding exponents. So that's u to the 3 halves minus, and then again, u to the half times 1, which is just u to the half or itself. Okay, so the only thing that I'm concerned about now is squeezing this on this page. But thankfully, we've been playing around enough with our checkerboard pattern in the rational exponents power rule video. So I'm going to try to finesse this hopefully in this bottom area. So here we'll have, I'll just squeeze it over here. We have 3 over 64. That's fine. And then we're going to take u to the 3 halves and add 1 to the exponent. So that's u to the 5 halves and then 2/5 according to the pattern I mentioned in an earlier video. Also, we have u to the 3 halves when you add 1 to the exponent here and then multiplied by 2/3. And don't forget your constant c. Okay, so now comes the moment of truth. We need to take that and reintroduce the quantity for u in terms of x. And that should be it. You could expand this out if you like. I don't really see a benefit to that, but just for a second, I'm going to play a little game here by shrinking all of this information because that's all old information. And maybe I can just get the answer now on one slide. Some of these questions I'm going to do in future videos. I don't know how I'm going to get them on one slide, but I don't want to, I like to do it on one slide, just like how you would write on a piece of paper. You wouldn't want to use or answer questions over more than one page, although I have done it myself. So should I expand this? I don't know. Do I feel like doing that? I don't see a benefit to doing it, but anyway, well, I'll just leave it in the factored form here. So, well, not fully factored, but at least in this form. Let's write here 2/5 And then u is equal to 8x minus x plus 1. Sorry, there we go, 8x plus 1. As you may know, I like to do these videos in one take, so it's a little bit funny to hear me talk and fumble my way through these questions. Just to let you know that the person behind the screen there is just a regular person that likes math, just like you. Anyway, you could expand this if you like. I'm going to leave it like that because you're just going to get big numbers and it's not really a huge takeaway for that. For example, here you'd have 6 and 320, and then 6 and 64 times 3, or 192. Okay, so let's move on to one more question, and hopefully nothing too nasty. I spoke too soon. However, we're not going to have that step that we had in the previous example. See this thing here? I call this recycling because it's like you're recycling the original substitution. In this case, though, there is something beautiful happening because the derivative of that will be a multiple of x right there. So this is good news. This question's easier than the previous one, provided that you're not scared of cube roots. So do you remember what a cube root is as an exponent? It's to the 1/3. Well, that's supposed to be a 3 there. There we go. Okay, let's do a substitution. We'll assume that u equals x squared plus 1 is a good decision. If that doesn't work, then we could always try something else, as I may cover in the future lesson. So differential form, the derivative of x squared plus 1 is 2x. And don't forget your dx. Well, taking a look at this example, we can see that there's a 2 instead of a 4. Does that really bother us? Not too much. So I'm going to just take a look piece by piece, or just quantity by quantity here. Let's start with the easy thing this time. You know, sometimes when you get stressed out, you do the easy thing first. So that's u to the 3rd. And now it's a matter of dealing with the leftovers here. We have here 4x dx. Oh, we have 2x dx. That's cool. Maybe if we just double that. That might be a good decision. Let's try that out, okay? I'm just going to double them both. You can do this lots of different ways. You could just ignore the 4 altogether, and then you would have your x dx is du over 2. But anyway, whatever you choose, it's all good. I'm going to double it because for me, that's just visually very, very pretty. There you go. See that? 4x dx. They match. And you're going to have 2 du, sorry. So let's put a 2 du here. The 2 looks a little bit out of place, but that's okay. Multiplication, we can do that. So anyway, there's your 2. The antiderivative of u to the 1/3 is u to the 4/3. And using that checkerboard pattern I've mentioned in earlier lessons, we would have 3/4 in the front. Now, this does simplify very well. I'll just do the following here. Let's do 2 times 3 divided by 4. Or if you want, just 3 over 2. And u to the 4/3. Let's deal with that as well. So u to the 4/3, well, u is just this. So we're going to have here x squared plus 1 all to the 4/3. Trying to get this more compact is really satisfying. That is the answer to this integral. And we'll move on to other techniques in future lessons. Thank you.